Welcome back everybody to Anything a Day project. Today we're going to solve a few questions on real analysis by Folland. So first one is 1.3.6. So for the question, just look at the book. It's written there. So I'm just going to solve it here. Let V be another extension of mu to m bar. I'll just call this m bar. Then for any E union F, where E is element of M and F is a subset of N for some, null set. And remember that mu bar E union F is mu E by definition that we use in the book. Then we can easily see that U bar E union F is mu. I've been keep saying it U, but it's actually mu. So yeah, so mu bar E union F is mu E, which is VE, as this is an extension, and this by the property is less than or equal to E union F, which is also by the property is equal to VE plus VF. And as we know that VF is 0, this means this is VE, which is mu E. So using this property, we know that this and this, so it's by this kind of like a sandwich theorem stuff. So we can easily see that V E union F is equal to mu E, which is just basically mu bar E union F. So the proof is done. So the measure is unique. Also, we're going to solve for 1.3.13. So mu is sigma finite. Then there exists, suppose there's an E, set E, such that mu E is infinity. Then by the property of the sigma finite condition, then there exists some EIs that intersect E, and these EJs are such that their unions are X, and this is a property of sigma finite, so it's in the book, you can check it. And we can easily see that at least one of these EIs will have a property such that EI intersection E is subset of E. This is of course trivial, and this will have a property such that it's bigger than 0, and mu EI intersection of E is a finite number. This holds because, first off, this cannot be infinite, because if it's infinite, because due to the fact that EI intersect E is smaller than EJ, and we know that mu of EJ is finite, so this can have to also be finite. So there's no cases where this is finite. And for this part, there has to be at least one EI intersection E that the measure is positive value, because if all of the EI intersection E has a 0 values, then we cannot have a condition such that mu E is infinite. So there should be at least one EI intersection E set such that their mu is bigger than 0 and is finite. So then the proof is done, and we can show that this measure is also semi-finite. Finally, we solve for 1.3.14. So we prove it by contradiction. So there exists C, some positive value such that mu E is infinite, and there's some F which is subset of E such that 0 is bigger than, mu f is bigger than 0, and this is actually smaller or equal to c. And this holds. And we'll show that this is, in fact, this leads to a contradiction, because if this is supposed to happen, then E minus F belongs to E, and this is also measurable by the property of measure. Well, to be more exact, it's a property of the algebra, sigma algebra condition. So this is also a measurable set, and this is a subset of E. And we can easily see that mu is an infinite measure, and this is same as mu F plus mu E minus EF, and this is due to the countable additivity. And we know that this is smaller or equal to C, and we'll assume that this is also smaller or equal to C, because we already said that there is a C where there's C such that every subset of E has to be smaller or equal to C. It's our condition. Otherwise, we can see that there's some set which has a measure that's bigger than C. So that's not what's going to happen. At least our assumption is. So this both has to be smaller than C. Then as C are finite, their sum is also going to be finite. So this has to be finite. But this contradiction, as this is infinite, but this shows that this part has to be finite. So it's a contradiction, which shows that there has to be some subset f of E such that it's bigger than C for any C. So it's like this. So the proof is done. And this is all for today, and thank you for again coming to Anything a Day.